Right, so we're at the top of the hour, so let's go ahead and get started. Let me share my screen. Lacey, can you confirm that you can see my screen?
Yep, looks good.
All right. So hi everyone and Happy New Year. This is the first i2X session since the year has started. So I hope everyone had a good break and everyone is keeping warm right now as we have a snowstorm going through the country. My name is Julia Matevosyan. I'm an Associate Director and Chief Engineer from Energy Systems Integration Group, or ESIG, and we are supporting this DOE i2X effort for the past couple of years. So just a reminder, if you're new here, the first half of this meeting is being recorded and maybe posted. So if you don't wish to be recorded, stay off camera and don't speak up. It's better if you don't speak up anyway, because we'll have presentation session. And then the second part of the meeting is not recorded, so you can speak freely and ask your questions. So the key goals of i2X First Forum is to facilitate understanding and adoption of new and recently updated standards that are relevant to existing and new interconnecting inverter-based resources. The forum convenes industry stakeholders to enable practical and harmonized implementation of these interconnection standards. I already spoke about parts of the presentations that are recorded and parts that are not. And additionally, the leadership team will produce a summary of each meeting where we capture recommendations and best practices, any challenges and gaps that were raised during the presentation. So if you missed some presentations previously or some meetings previously, you can go to i2X webpage and read the synopsis, or also look at the materials and previous recordings. So just a little bit about our leadership team. We have Cynthia Bothwell from Boston Government Services, contractor for DOE. Robert Reedy from Lindell Reed, who is contractor for DOE, Will Gorman from Lawrence Berkeley National Lab, Jens Boehmer from Electric Power Research Institute, or EPRI, myself from ESIG, and Ryan Klimt from Elevate Energy Consulting. So just a summary of the last meeting. As I mentioned, the last one we had in December, so it's almost a month and a half ago. We were talking about IBR plant commissioning best practices. And so we heard from IBR developer and their perspective and what are the best practices when commissioning a plant, power plant controller perspective, so manufacturer perspective. So that was a unique point of view. We haven't had PPC vendors before on our forum. ISO perspective, where we heard from IESO and how they are doing commissioning and what they're looking for in their commissioning testing. And then we had Q&A and structured discussion, as always, and you have a link here on the slide to the meeting summary, recording, and presentations, and I believe Lacey already put the link in the chat. So just key themes from the last meeting. Commissioning is a critical reliability gate, and this is the last chance to verify reliable operation of an IBR plant before it reaches its commercial operation date. If there are any fixes that are needed post-commercial operation date, these fixes are pretty costly, so it's better to treat commissioning as grid reliability risk checkpoint. Inconsistent requirement lead to uneven rigor. There is a wide variety of what's required during commissioning testing, verification, and performance validation. And so even if NERC standards around commissioning testing do not exist, or if in your area there are no robust commissioning test requirements, it's still essential to do this testing, even for the sake of plant operating reliably and not having issues after commissioning. Just doing a set of standard tests misses real world conditions. So just doing regular AVR PFR containment tests that are normally required is maybe insufficient, and you need to test failure modes, for example, communication failures, or some edge cases, for example, providing reactive at zero power operation to just ensure that the plant works as intended. And it often gives some insights to even plant developers, plant owners, to understand, if something's gone wrong or done wrong during plant design. Model must match as built performance. So as we hear times and times again, study models often diverge from field implementation. And so validation and commissioning, even though it's limited to the set of tests that has been done, is still very valuable. And then lifecycle updates are needed to ensure that the plant continues to reflect that the plant model continues to reflect what actually is happening in the plant and how the plant is set. And then end-to-end integration is essential. So reliable operation requires coordinated control, SCADA, communications, and telemetry, and early and disciplined end-to-end commissioning reduces risks and delays, and then reworks after the COD. So these are just kind of main key themes of the last meeting. And again, I strongly encourage you to go back and look at the materials if you missed the meeting. So about upcoming meetings, so we are now on January 27th, and we'll be having this discussion around NERC PRC-029 implementation. For February 24th meeting, we are still debating what to talk about. So I've already started Slido poll on slido.com, use event code first9, and you can propose a topic. So if you think we haven't covered something, you're interested to hear about something more, please let us know, and it will help us to inform the next meeting. And then for March 16th meeting, many of you, when I ran this kind of requirement of or this poll of what you would like to hear in 2025, many people mentioned grid forming, and so on March 16th, we are holding one-day grid forming workshop. It's going to be a hybrid event, so you can attend virtually or attend in person. This is at the front end of our ESIG spring workshop that will hold that week in Tucson, Arizona. And so the agenda of the workshop is already posted. We'll talk about what grid forming even is. So there'll be a session just talking about basics of grid forming. We'll talk about what is the need for grid forming inverter-based resources, what are specifications that are already being published by different system operators and other organizations, and then we'll have a session around projects that are already on the ground and lessons learned from deploying this project. So again, I think it's going to be a very interesting event, and I highly encourage you to attend either in person or virtually. And again, some links to where we post all materials from our previous events. So let's switch gears to what we are about to talk today. As you probably know, NERC PRC-029 was approved last year by NERC, and so currently there is some work going on in implementation of the standard. And what we would like to focus on today is specifically related to existing plants and plants that are in flight, so currently in the interconnection process, that PRC-029 will also apply to, and everyone needs to go and evaluate if their plants are able to conform with PRC-029 or if there's a need for exemptions. And so for today's agenda, we'll have JP Skeath from NERC, providing us recap on PRC-029 and where we at with implementation and FERC Order 909. Then we'll hear OEM perspective from GE Vernova, from Jo and Lucas, and they will talk about their perspective and also recommended best practices as people are evaluating existing equipment and its capabilities to conform with PRC-029. And then last but not least, we'll hear from Amin from Elevate Energy Consulting. The company is working a lot right now with plant owners and developers, trying to kind of understand how to go through this evaluation process and show conformity with 28 with PRC 29, and also if any exemptions are needed. So as such, they work with many generator owners, and we have invited them to present on the best practices. And then we'll have Q&A session, so you can start posting your questions as people presenting, and we'll take all the questions after the presentations have finished. And if we have time, we'll have some structured discussions around additional questions on PRC 29 implementation that we've prepared. So with that, here are some good rules on how to behave during the meeting. Please use slido.com to post your questions. You can upvote questions that are already there. That helps us to prioritize. So do that rather than repeating the question that has already been posted. Don't be shy. Please put your questions as we go, and we'll address them all after the presentations are over. And without any further ado, JP, I'll give it over to you.
Thanks all. I'll start to share my screen here. All righty. So
I can see your screen, JP.
Perfect.
So you're good.
Thank you, Julia. I was going to quickly ask that, but I'm JP Skeath, the manager of engineering and security integration over at NERC. I'm on the engineering half of that equation. So a lot of this will just be on the just the engineering perspectives. If you are going to ask about security integration, that's another person inside NERC. Thanks for having me for this overview of the PRC-029, PRC-29's development related to FERC Order 901, as well as the ongoing interactions with FERC Order 909. So today, I am going to share with you how we came to this ride-through based standard, talk about some of the exemptions and the design criteria, and then kind of share with where NERC's going from in terms of revisions to that standard in particular. So PRC-29 was developed as part of a 4-milestone goal from FERC Order 901. The first milestone is largely just the work plan associated with the remaining milestones to address all the directives within FERC Order 901. And FERC Order 901 was released coincidentally with the IBR registration initiative that is also in response to a FERC order that essentially says we need to register additional inverter-based resources in order to ensure the reliable performance of the aggregate fleet of inverter-based resources on the bulk system. So this is developed as part of the standards revisions to address the performance that is expected of registered IBR categories. So PRC-29 was in milestone 2, so that was due to the FERC commission by November 4th of 2024. And it included a few other standards that I'll review in just a second, but we have already completed milestone 3 and are in process for milestone 4. So we are talking about a standard that has been developed a few years back in terms of its development, but is undergoing revisions based on the subsequent edits in these milestones, conversations and standards, as well as FERC Order 909. But that kind of sets the context of where PRC-29 was developed and under what kind of assets are we really talking about. And that includes the information and findings learned from the IBR registration initiative. So milestone 2 carried with it 3 separate standards, or new standards here. The PRC 28, 29, and 30. And so the other parts of milestone 2 were to install monitoring specific devices within the generation fleet, PRC 29, which I'll go over in a bit, and PRC 30, which was generator owners having an analysis of root cause during a disturbance and to evaluate the ride-through performance of specific generators when certain reductions are seen at the plant level. In PRC 29, identified very specific performance-based ride-through criteria for voltage or frequency excursions with some processes on the exception. That standard sets the expectation for inverter-based resource interactions with the transmission system or the bulk power system, and has kind of separated on out the ride-through type characteristics or any sort of protection-based performance for disturbance ride through from its synchronous counterparts in PRC 24. So we'll kind of go through. I have on here just the slides of the last and final ballot for each of these. PRC 29 did have to go through a NERC Board of Trustees 321 process to get it through the finish line. But these are the percentages of final ballot for each of the new standards within milestone 2. So that kind of shares the context that these particular ride-through performance criteria were developed, did reach a heavy consensus in their final state, but did have quite a few of development proceedings to get to the final language for voltage, frequency ride-through performance, and the exemption type process. And I'll speak later as to even additional concerns and comments that were raised in the FERC Order 909 and 909A. So let's start where it is probably best to start from, in the beginning. And so I basically set the context that this standard was developed with Order 901, and FERC Order 901 identified that IBR ride-through models and additional issues in planning and studies dominated the IBR fleet. This was released in October of 2023 and directed NERC to develop specific standards to address the reliability issues at all stages of interconnection, planning, and operations. I overviewed those 4 milestones. One was the work plan, and milestones 2 and 4 being those particular standards. This order itself cites a plethora of disturbance reports from NERC that significantly highlight and show the state of the land as system disturbance occurs, inverter-based resources trip on some or various other protective mechanisms to the plant or settings or a variety of different root causes. And that led to a significant reduction of exchange of current as seen by the bulk power system. And so the order highlights in various different methods, roles that the ride-through behavior of inverter-based resources needs to become standardized. And so PRC 29 does that. Here are some of the highlighted sections for FERC Order 901 that really describe the need for standards reform and making sure that there is sufficient ride-through characteristics and performance from inverter-based resources. I'm not going to read everything that's here on the screen. I'm just going to highlight a few of the surrounding text. This is cited from FERC Order 901, paragraph 190. The first bullet essentially is saying that the registered IBR owners and generators, generator owners and operators to use that appropriate settings and general plant type coordination, as you can see listed in the various items here, to ride through frequency and voltage system disturbances, and has a very small subset of permitting of IBR tripping, and that's only to protect the IBR equipment in scenarios similar to synchronous generation resources, as using a protection from internal type faults. Additionally, the order required that the IBRs were continuing to inject current and perform frequency support during the bulk power system disturbance, that is, riding through the disturbance rather than separating on out from the rest of the bulk power system. Further, they've said that there was need to be a prohibition of momentary cessation and a no trip zone during disturbances, and that you can kind of see kind of calls into some of the IEEE 2800 language of certain zones of operation and expectations during those zones. And the last bullet I have to cite from P190 is that there's frequency and voltage ride-through expectations in these new and or modified reliability standards, as well as that address the phase lock loop synchronization issues and other known causes of IBR tripping or momentary cessation. And so that's what PRC 29 aimed to address in terms of changing to meet the FERC order directives. I also wanted to cite that there was some potential exemptions that were already baked into the 901 language. Those are limited and documented exceptions for certain registered IBRs. They concluded the sentence from voltage ride-through performance requirements, but the additional bullet I want to have here is that it's for existing IBRs that are unable to modify their coordinated protection and control settings in order to meet those requirements. And so you can see that FERC in the language already identified a limited set of exemptions are probably going to be necessary to handle legacy inverters that just cannot be updated to meet the expected ride-through settings, as those settings were not really standardized during that time, and there wasn't a NERC standard that we could point to. PRC-029-1 is that standard today, as it's been approved by the commission. However, you can see that the exemption process is designed to meet this directive, and that's cited in paragraph 193. Further, in paragraph 199, the commission states that to the extent NERC determines that a limited and documented exemption for those registered IBRs currently in operation that are unable to meet ride-through requirements is appropriate due to the inability to modify coordinated protection and control settings. So they just kind of reiterate over and over, it's that the limitation of exemption is designed around the inverter-based resource essentially has done everything in good faith to meet the ride-through requirements, but equipment at the site cannot meet certain portions of the ride-through settings. And so that's what the process we have in PRC-29 is. So this was developed as the IBR counterpart to synchronous generator performance from PRC-24. PRC-24 is largely a relay setting for frequency and voltage protected devices for synchronous facilities. And so this is a defined ride-through, which is a little bit dissimilar from PRC-24, as PRC-24 focuses on settings in the protective equipment, whereas PRC-29 looks at the performance as seen at a certain point in the plant for exchange of current and ride-through type behavior. But it essentially looks at frequency and voltage, and they're very similar in the goal is to ensure certain performance from those types of resources. So it used PRC-29 as its starting point and reflection for the as similar to synchronous resources, and then altered it to meet the expectations in the directives of 901. There's 4 requirements in PRC-29. And so requirements 1 to 3 establish the frequency and voltage ride-through requirements, graphs, charts, etc. For the inverter-based resources. Requirement 4 is the exemption process, and that is how we're going to treat and the requirements expected of seeking an exemption from Rs 1 through 3. So R4 applies to IBRs in service by PRC-29-1 effective date 10/1/26, and it's for known hardware limitations that prevent the IBR from meeting documented frequency or voltage ride-through criteria. So that process needs to be submitted to your compliance enforcement authority, planning coordinator, TP, TOP, and RC. So I realize I need to probably spell out the transmission planner, transmission operator, and reliability coordinator. And it only is, sorry, I should say the notification is to give the planning entities, your planning coordinator, transmission planner, and your operating entities, transmission operator, and a reliability coordinator, that this particular plant is known to not meet the entirety of the ride-through expectation, so that way all planning and operating entities are aware that the ride-through performance of this particular plant is going to differ from the standardized performance as seen in PRC-29. The owner of that IBR is also required in that exemption process for follow-up requests on additional information. Those are likely to come from the planning coordinator, transmission planner, transmission operator, or reliability coordinator to make sure that any additional information for their study purposes in planning or operations is required. And then if the CEA accepts the hardware limitation, the IBR owner has to notify the PCTP, TOP, and RC, those entities, within 90 days to make sure that they're aware that this limitation was sought and is approved by the CEA. So that's the broad overview of PRC-29. But I'm going to go deep into these specific requirements to really show where the specific item is identified. So R1, I'm not citing the actual standard language, but giving a broad overview. Is requiring the generator owner to design and meet or exceed the ride-through except in certain scenarios. And so we've identified already that we're establishing the owner of an IBR shall meet or exceed ride-through under the normal operating state, except for these operating states, and that is to clear the fault, the voltage is outside of hardware limits, and that has ties to the R4 exemption process. Instantaneous positive sequence phase angle shift to 25 degrees or higher measured at the high side of your main power transformer. Voltage per hertz that exceed 1.1 per unit for 45 seconds or 1.18 per unit for 2 seconds. And so those are the limited exemptions that are broadly applied. And so if there is a hardware limit, that's when R4 really comes in. So R2 is the follow-up of R1 that defines the exact voltage ride-through expectations. So the owner of the IBR shall design or meet those voltage performance. And I have a chart here on the next slide to really show what those voltage performance markers are. And R3 is the frequency counterpart that says you shall design or meet or exceed the specified frequency performance. And I believe there's just a very limited subset that is a broad application. R4 is that exemption process for in-service IBRs with hardware limits. So let's take a look at the voltage and frequency curves. The voltage is graphed in a curve in the standard, but is in tabular form. So is the frequency, but we did draw the frequency in the standard attachment. So table 1 is for those AC connected wind IBR voltage. Table 2 is then the voltage requirements for all other inverter-based resources. This is important as NERC's definition of inverter-based resource excludes type 1 and type 2 wind, but does include type 3 and type 4 wind plants. And so type 3, which has an AC connection in the facility, has a little bit different expectations in the voltage ride-through. However, you can see the only major difference between these two charts is going to be in the lower voltage limits, where you have the less than 90 or less than 0.9 per unit being roughly about half that of all other IBRs. But if you plot this on out, the only differences you'll see is under these very low and shallower type voltage curves. But those are the curves in attachment 1. Those specify the expectations at measured at the high side of your main power transformer for the for the facility to ride through or to continue to exchange current during the disturbance. On the right-hand side, you can see the frequency counterpart, and so it's a fairly square box. You have a 57 and a 61.6 that goes out to about 299, 300 seconds, so less up to 300 seconds. And the other is a indefinite ride through where we have, I forget the exact value here, and I would have to take a look at the standard, but I think that's 61.2 and the 58.9 or really close to 59 hertz there, as those are to be a little bit beyond the expected over frequency and under frequency load shedding to ensure that there's a ride through in that last little safety net, so that we're not shedding load in addition to also not expecting generation to go through. But those are the charts for the expected ride through. And I'm going to delve just deeper into the exemption process that's baked into PRC-29. We do require quite a significant portion of data in order to achieve an exemption. So we would need information about the IBR, so the name and facility number, the specific aspects of the ride-through requirements that are not able to be met, voltage or frequency, that specific pieces of hardware that are performing that limit, and technical documentation verifying that that limit is due to hardware that needs to be physically replaced to meet all the ride-through criteria, that the limitation cannot be remedied by software updates or setting changes, to really specify that, yes, this is a true hardware limit. It is not something that just simple settings or changes are able to address, and that it is a limitation of the hardware itself. And then any information on plans to remedy the hardware, for example, any expected or estimated dates on when this limitation is planned to be, for whatever reason, no longer applicable because the hardware has been replaced. The duration of this exemption is essentially indefinite, in that as long as within that 12 months of submission within PRC-29's effective date, if the hardware is not replaced, that exemption still stands as the hardware is still present. However, if that hardware is replaced, the exemption ends, and notify those entities in the previous slide within 90 days needs to occur for that exemption process. After the development of PRC 29, we were issued FERC Order 909, which approved PRC 29-1 and PRC 24-4, so the counterpart for the synchronous facilities was also filed at the same time, but it also included several directives to NERC. And so on August 28th, and that's 2026, sorry, no, that's a typo there. There are a few requirements. Paragraph 87 says that we need to address the issues raised in the rulemaking proceeding for FERC Order 909 regarding HVDC connected IBRs with choppers and long lead time equipment, and to submit its determination, NERC's determination, within 12 months. In paragraphs 107 to 108, we also have to address the concern about the absent documentation for legacy units to have a few examples they opined on, and that needs to also be included within that 12 months. Following the full implementation of those, we also then need to submit an informational filing, including the certain data and assessment of the reliability impacts of the exemption process that's been finalized in the revisions to PRC 29-1. 909A was issued just a few months after 909, and that just is regarding this timing mismatch between PRC 29-1 and a revised standard to suggests to NERC to use enforcement discretion for any sort of timing mismatches that are set in PRC 29-1's implementation schedule and the revised standard, so that we're able to move forward in a very productive manner without directing any sort of revisions to implementation plans, etc. NERC then, while you can kind of see the dates here, is we were issued 909 in July, set up a virtual conference in November, and there was a September issuance of 909A. This virtual workshop is recorded, the link's here on the slide, and that largely focused on three broad topics: the clarification on documentation obligations for legacy IBRs, the equipment limitations of HVDC IBRs with choppers, and equipment limitations of long lead time projects. These are gone in extent in the link. So the keys that we can take away from each of these was that entities are doing good faith efforts to find the most amount of documentation available, and they're producing an entire packet of information. So it's not just one hardware specification they're looking at. They're trying to do as much as they can to gather the on-site installed parameters and build a document package to send to the CEA for any legacy IBRs seeking exemption. And that was generally the expectation to kind of move forward. There was some conversation about EMT validation or verification, but most of the consensus that was built there was to not require EMT models or EMT-based or simulation or verification that goes into the minor nuances to verify ride-through, but rather looking at the plan as a whole, and the expectations as seen at the high side of the main power transformer, which could include simulations, but where that does not see profit, there's other documentation that was gone over in that panel to address the concern. Further, we had two other panels that were more the equipment limitations of choppers, and then the expectation of what the long lead time projects were. The chopper panel generally went and understood that there are thermal limitations of the multiple successive ride-through events, and so that there is a technical concern with successive events that kind of go between a lot of these ride-through faults. And so if you have multiple faults within a small time window, what's the really expectation, as there is equipment limitations on the thermal dissipation, and that's not really well considered within the current PRC 29-1. That panel was very fruitful in identifying ways to move forward in revisions for 909. The last panel was the equipment limitations of the long lead time projects, and generally what is there was quite a bit of nuanced opinion and different opinion in that panel. But in general, the panelists and NERC staff generally took away that there is a certain period of time where an agreement is in place, but it takes a very long time for the construction project to finish. And so if we're talking in-service dates for the expected ride-through, that is beyond the actual implementation of PRC-29. But the requirements were agreed upon and signed prior to. And so we're just trying to find the exact date and agreement to make sure that the long lead time projects are not expected to become part of this retroactive applicability or treated as a new installation when in fact they are a legacy or in-flight type project. And so that was very fruitful. While we were hosting this, we had, through our process, an industry received SAR. You can kind of see the date here is October, the 909 conference being a month later. This SAR, with the findings from 909, are the initiation of Project 2025-05 to address the concerns that we heard from 909, the industry feedback from the webinar, and this SAR in particular. This SAR was posted for a comment that ended late last year, and the standard drafting team nominations are closed. So we have a team that's designed to take these comments that we received from industry and revise the SAR accordingly. The scope of this is very much aligned with what we heard in FERC 909, and that is to extend the PRC-29-1 R4 requirement exemption eligibility to include the long lead time projects in active development, extending the exemptions to include chopper limitations, and so HVDC or AC related choppers, as well as clarifying the non-exhaustive acceptable evidence to aid entities. And so that addresses the obligation or document obligations as considered in the panel for 909, as well as the 909 text itself. So if you want to get plugged in, there's ways to monitor this. Linked here is the Project 2025-05 ride-through revisions standard that is under active development. The link is below. This may require you to have a NERC portal account in order to get added to like distribution lists, etc. But the page postings for anything public will come to this page. So more than happy to help in terms of getting you to the right place if you are still interested to continue the ongoing work. But this is still in very recent active development. So I believe I hit my time marks with a few minutes to spare, Julia, but I'll turn it back to you.
Thanks so much, JP. We'll move on to Yo and Lucas to talk about OEM perspective, as they started already working on PRC-29 implementation and evaluating the equipment for conformity or compliance with PRC-29. I would like to ask the audience to please put your questions in audience Q&A because people put their questions in the poll for future topics. I'll read out those questions still, but going forward, please put your questions in audience Q&A. Use Slido with the event code FIRST9. And so let's go ahead and move to Vernova presentation. And guys, if you could introduce yourself first.
Okay, can you hear me, Julia?
Yeah, your screen was there, and then you pressed stop sharing, and that stopped. I think you maybe wanted to hide the bar of sharing, but accidentally stopped the sharing. Coming up. Yeah, if you want to get rid of this, you can just press on hide.
Got it.
There you go.
Okay, so good morning, everyone, and thank you for making the time. I'm Akpaloo. I'm the product manager for grid integration and wind control at GE Vernova. My role sits in that intersection of product strategy, engineering, grid requirements. So my focus is translating, evolving grid requirements into practical deployable capabilities for our customers. Joining me is Lucas Sales, who jump in where deeper technical context is helpful. Lucas, you want to introduce yourself?
Yes, of course. Hi, everyone. As you all mentioned, I'm Lucas. I'm a systems engineer responsible for implementing both the PRC-29 and also many of the IEEE 2800 new requirements to the GE Vernova wind turbine platforms. So glad to be here and help in the discussion today.
Right. So let me start with where our products stand today. So at a high level, our new platforms are in a strong position. Our 2X 127s, 3X, 6X fleets were designed with modern grid requirements in mind. So where units are already operating, software upgrades allows us to fully align behavior with PRC 29 and IEEE 28 expectations. So when we look at the legacy, I think I'm not sharing. Okay. So when we look at the legacy fleet, the story is still very constructive across our 1X, 2Xs, and early 1X platforms. Most requirements are achievable through targeted software upgrades. For the older variants, capability expansion is very real. It's just aligned to turbine design and configuration. So the key message here is this: across the fleet, there is clear upgrade-enabled path to enhance grid capability, and it's not a one-size-fits-all, but it's a practical and scalable movement. Lucas, you want to add something on slide 1?
Yeah, mainly just if anyone isn't necessarily familiar, when we're referring to 2X 127, those are our 2 megawatt and beyond platforms with 127 meter rotor diameters, and 3X would be 3 megawatt and CX 6 megawatt. Likewise, the legacy platforms 1X would be normally 1 megawatt platforms with generally smaller rotors. Key thing here to notice is that, as you all mentioned, we are able to enhance in some of these platforms. We do have line of sight of expanding the capability of many of the requirements, not necessarily always fully meeting for these very legacy platforms, but I still being able to drive the grid to a better reliability.
Okay, thanks. So the natural question we get is, okay, how do we actually work through this? How do we support our customers? And I say we support them in various concrete ways. First, capability and clarity. We provide position papers and technical capability reports that clearly explain what eTurbine can do today, what upgrades unlock, and where physical limits exist. So that creates a shared technical baseline for generator owners, consultants, and regulators. We also develop validated turbine models, which includes the PSSE, PSCAD, that reflect both current behavior and upgraded controls. And these are designed to plug directly into plant-level interconnection studies, while still respecting the ISO and utility-specific processes. Lastly, software upgrades are done the right way. We follow the structured platform-based roadmap. They are validated thoroughly and deployed collaboratively, aligned with outages, operations, and regulatory milestones. So the theme here, I'll say, is coordination on how we support our customers. Lucas, you have anything on this slide, or can I move on?
Yeah, I think it's worth mentioning that I know multiple times we talk about requirements, and we think that moving protection settings out of the way and or just updating control settings is enough. But the reality is that with this harsher requirements, for which especially the legacy platforms haven't been originally designed for, moving protection settings out of the way isn't enough. So in multiple times, this requires the OEM ourselves to revisit the original control strategies, assess, let's say, damage curves, and in some cases actually have to create new control features that would allow us to ride through these expanded or harsher requirements. And in most of the cases, we are able to do that with software upgrade only. But worth mentioning that in some cases, these could require some sort of a hardware upgrades. This is why one of the reasons why I always mentioning that Vernova works on issuing these technical capability reports, so that our customers and the generator owners for these platforms would be able to understand what are the limitations, what are the opportunities that each platform has to meet all of these requirements.
Yes. So now let me spend a minute on what we are seeing across the industry because this isn't unique to any one OEM or customer. There's ongoing alignment around timing, particularly on how PRC-29 R1 to R3 enforcement relates to PRC-28 implementation milestones for in-service plants. On maximization, I'd say that ERCOT is more explicit today, while the broader NERC guidance continues to mature, making turbine-level capability documentation even more important. We are also seeing continued discussion around exemptions, especially for in-kind replacements and partial repowering scenarios, and what constitutes sufficient justification when physical constraints exist. Finally, upgrade and model validation processes still vary by ISO and utility. And I'll say that variability is exactly why standardized upgrade pathways and OEM-supported documentation really matter, especially for customers managing large multi-region portfolios. Some of the questions that come up may be like, does replacing one out of a number of limiting hardware components still keep the exemption valid? Lucas, want to chime in on here?
Yeah, in this specific example, I think this is one of the items that many customers who are going through repowering of their platforms have questions about. One that isn't necessarily, that while PRC-29 states that the exemptions are valid until the limiting hardware isn't replaced. With repowers and every different repower, and by repower, I mean it could be switching the rotor diameter of a given wind turbine, it could be replacing different hardware. So essentially, many of our customers have this type of questions on whether their exemptions would remain valid or not. And in some cases, this is a very site-specific basis type of answer, as each repower may change different hardware in different turbine platforms. So not a super clear answer we can give right away until we fully understand what is the scope of each repower. And just another worth mentioning comment here on the maximization requirements. As you commented, this isn't a written requirement on PRC-29 that was much more clear on the ERCOT NOGAR 245 last year requirements, but we within Vernova are working towards whenever a requirement for legacy platforms can't be fully met, we are still developing the solutions that would allow a requirement to be, it should be maximized from the original capability that would have been published in the past, and still is showing the, let's say, in the leap of faith that is all bringing the grid to a better capability and reliability, even though that is not necessarily the clear requirement from a PRC-29.
Okay, so where does this leave us? From our perspective at GE Vernova, the path forward is actually quite clear. We stay transparent. We are very deliberate about clearly communicating what each turbine platform can do today, what can be unlocked through software, and where physical limits exist. And that transparency is what builds trust and enables good decisions. We also continue to lead with software. So wherever capability can be expanded through controls and system level enhancements, that's where we focus, because this is scalable, it's faster to deploy, and it minimizes disruption to operations. We support risk-informed compatibility strategies. And when I say this, that means helping customers and stakeholders focus on what matters most for system reliability, using validated models, measure data where available, and practical technical justification, rather than just treating every case as binary. And just as importantly, we make sure customers have the right tools in hand, validated models, clear documentation, and technical insights that can be used confidently in studies, discussions with ISOs, and regulatory reviews. So what we've consistently seen is that early coordination always makes a real difference. So when generator owners, OEMs, consultants, the regulators engage early, it creates clarity, it aligns expectations, and leads to much more smoother execution, especially at the scale we are talking about. So as guidance, testing, expectations, and interpretations continue to evolve, we'll stay actively engaged. We'll keep refining our assessments, aligning on practical implementation pathways, and supporting customers every step of the way as they navigate this transition. So the goal here is simple: practical outcomes, scalable solutions, and confidence in the forward path. Lucas, you want to add something before we open up the floor or hand over to Julia?
No, I think this is a good summary for this one. Yeah, nothing to add here.
Okay, thank you, Julia. I want to hand over to you
All
right
right.
now.
Excellent. Thanks so much, Yo. Thanks so much, Lucas. Again, encourage everyone to put your questions in Slido, slido.com using event code first9. And let's go ahead and switch gears to generator owner developer perspective that Amin will present. Go ahead, Amin.
All right. Thank you, Julia. Let me share my screen.
Perfect.
All right. Thank you. And hi, everyone. I'm Amin. I'm a senior power systems engineer at Elevate Energy Consulting. Yeah, thank you for having me here. And today I want to talk about our experience supporting generator owners and IBR developers with the studies around NERC PRC-029. And we've done quite a few studies last year and this year, and would be glad to share some of the lessons that we learned doing these studies with the audience here, and I hope you find it helpful. Before I get to the technical section of my presentation, I just want to highlight some compliance deadlines for PRC-029. I'm not going to go into details of each requirement. I think JP spent very good time on explaining details of each requirement, but as a consultant, we've seen that IBR owners as well as developers come to us when one deadline is approaching and there isn't like sufficient time left to do the analysis and like ensure compliance. So I want to highlight this, that PRC-029 is gonna has gone into action since October 2026. Is gonna go into action, sorry. And the deadline for design evaluation compliance for BSIBRs is October 1st. And for non-BSIBRs is January 1st, 2027. So it's around like 11 to 12 months left to show your compliance. And it's gonna take time to like collect data, to do the analysis, find out those non-compliant items, and then coming up with actions to address those, find hardware limitations, and file an exemption. Like all of these are gonna take quite some time. So our recommendation is to start thinking about PRC-029 as soon as possible because these deadlines are approaching. And then moving to the assessment methodology and lessons learned, I want to firstly acknowledge that these slides are how we see PRC-029 and is our understanding. And we are always open to learn and feedback and try to constantly improve our assessment methodology. So feel free to give us comments and speak up like about your experience doing PRC-029 studies, because we also find it very helpful to improve our assessments as well. So at Elevate, what we like, how we do PRC-029 is firstly the design evaluation part, which involves several steps, and they're shown here. One first step, which is very important, is to gather as much as data that is available about that IBR site. And once that data is available and something is not there, so we're going to coordinate with the OEMs to find out if we can have that information that's needed for doing a PRC-029 study. And then we're going to do a very quick check about different settings or like information that we have and see if the IBR model have those settings implemented correctly. And then we're going to get to like the stage of evaluation for the site configuration, do a quick model sanity check, and then start running simulations. We have around like 8 to 10 simulation cases that we run for PRC-29. And then once those simulation results are analyzed, we're going to come up with like if any update is needed in the plant, or what corrective actions can be to address those non-compliant items. And then help the client with filing for exemption requests if there is any hardware limitation, and also help them put together a compliance documentation package that can be submitted to NERC. So in my presentation, I'm going to be focusing on this part mostly, and these two specifically, to just give an idea of like how PRC-29 study can be done, and as like one approach that we are doing at Elevate. As I said, the first step, which is a very important step, is data collection and preparation. So for PRC-29, there are a few items that are required and very necessary to be able to even start like an evaluation of the plant. And that would include, firstly, the as left settings of the voltage and frequency protection across the plant. And that would include the inverters, the relays on the HV side of MPT, feeder relays, substation relays, if there is any shunt reactors or like cap banks, under voltage, over voltage element, like all those settings are required for PRC-29 study. The other piece is an accurate and working model. That can be either an EMT model or a phasor-based or RMS model. And PRC-29 can be evaluated in these two types of softwares. And the final piece, I would say, is the inverter manual that has the PQ curve of the inverters and the capability. That's also needed because PRC-29 has certain requirements, especially like R2.2 and R2.3, that talks about whether reactive power is within the hardware limits of the inverter. So that information is also needed. Anything else in addition to these can be helpful. I've listed some of them here, like SLD of the plant, any MQT report, any PRC-24 report, like control narrative. This can also help us to understand the right-through behavior of the plant in a more comprehensive approach. Once we have all this information, we're going to do a check of the model and its configuration to make sure that any setting in that PSSC or PSCAT file matches exactly what's in the field. Since we want to have like a good confidence in our model before starting to run the simulation. And if we find any discrepancy, which is the case, like I would say like 60% of the cases, we're going to document that and talk to the client about it. And if they give us a green flag, we're going to go ahead and change that. If it's something small or if it's something big, we're going to reach out to the OEM or the entity in charge of that equipment to find out how we can address that discrepancy. Once we have a good model, we're going to go ahead and start the simulations. And that would include like 2 steps. Firstly, setting up the load flow cases and then start running different sets of tests specifically designed for each of the requirements in PRC-29. And once that's done, then we're going to start analyzing the simulation results and evaluate if each requirement is passed or failed, and then come up with recommendation on how to address those failures. As an example, change relay settings, I don't know, like add a new component or change PPC settings, or if there is a hardware limitation, like how to file an exemption, and then the final output is going to be a report. Now, going into more details of how we can do a sanity check of the PSCAD or PSSC model or PSLF model versus the left setting. So the first approach is to check like everything with these left settings of the field, but I wanted to highlight a few items that are important for a PRC-29 study. So the first item, as I said, is the under voltage, over voltage, and under frequency and over frequency settings of the components across the plant. And that would include the inverter, feeder relays, cap banks and shunt reactors, any HV substation relay, since these are going to determine and have like direct impact on the right-through performance of the plant. So these elements are very important to check and make sure that they match the as left settings in the field. Now going to the inverters, like some other items that you can check and to make sure that they match what's in the field can be the right-through curve of the inverters, LVRT curve, HVRT curve, the active reactive current priority, maximum current capacity, Imax of the inverter, the VRT mode, if they're following K-factor, if they're following some other control strategy, and any information about the current limiter setting, because that's going to determine how much reactive current is curtailed to, or active current is curtailed, and it's going to impact evaluation of requirements R2.1 and R2.2 in PRC-29. Then moving to the PPC, in PPC, it's good to look at active reactive power controller gains and like what type of controller is used. If there is any ramp rate limit or settling time on the active power or reactive power, this is like for requirements R2.4 and R2.5. The VRT settings of the PPC and where the PPC is controlling like different quantities. And we've seen a lot of cases where that control point is not accurately set in the PSSC model, let's say. PPC is controlling POM or POI, but it's the other way around in the PSSC model. So we want to make sure that all of those match what's in the field. And also for the MPT, like the tap changer setting is very important, like which side of MPT that tap is controlling, and what's the default setting that's in the field for that tap. And then once we have done these checks and we have a good confidence in our model, then second step is to set up our power flow case. And for this, what we do is that we consider the worst case scenarios. And the reason for that is to push the IBR as close as possible to its current limit. And we want to evaluate the IBR right-through performance around that worst case scenario. And that would be rated active power and maximum reactive power generation. And for almost like 90% of the plants across North America and ISOs and utilities, maximum Q is at 0.95 lagging and leading power factors at POI. And that's what we consider for our studies to make sure that we are not going beyond what's required for the IBR plant at POI. If the plant is connected to like an area that has a different power factor requirement, so you can consider that as the worst case. But as I said, like 90% of the cases, it's 0.95 lagging and leading. And another consideration, which is very important to have in mind, is that for the lagging case, make sure to keep the cap banks in service if there is any cap bank in the plant, and set the shunt reactors out of service. And the reason for this is that you want your cases to be realistic as well. And if an IBR site is going to operate it at Q max, then the first option is to use the cap banks in the plant and don't use the inverters to generate Q and get closer to their current limits. And you want to put the shunt reactors out of service and do the opposite for the leading case. And this is going to make your case realistic as well. Another very important factor that I've seen a lot that when setting up the load flow cases, many people do it wrong, is that when setting the lagging and leading case, make sure that the voltages across the plant remain within 5% of the rated voltage. If you are increasing Q generation of the inverters, and you see that the voltage at the inverter terminal goes to, let's say, 1.1, then that means that that plant is not able to meet 0.95 lagging power factor. So you may want to end up at a larger power factor, let's say 0.99 or 0.98, and that would be your worst case scenario rather than 0.95. Another factor that when setting up your load flow case in PSSC and PSLF, specifically, is that this 0.95 lagging and leading apply to POI, but PRC-29 applies to POM. So if I go back here, this is POI where we're going to have 0.95 lagging and leading power factors, and this is where POM is and where PRC-29 is applicable. So when setting up your power flow case, you solve it for 0.95 at this point. And then when you want to connect your generator or playback function to this POM, you're going to remove this tie line. And if you solve your power flow again, then the P, Q, and V that you calculated here is going to change. So it's important to maintain that power flow solution that you got for solving 0.95 at POI. So most of the cases, that's not going to impact the result since this impedance is not that large, but we've seen cases that this impedance for the tie line has had very large charging current. So you want to make sure to capture that P, Q, and V that you got from the solution for 0.95 at POI. And then finally, make sure to reset the tap value every time that you solve a power flow case, and specifically in PSSC and PSLF. Since that tap changer is going to regulate the MV side voltage. And when you are trying to set up 0.95 lagging and leading cases, you may see over voltage, but you have not reset the tap. And when you do that, that over voltage is going to be gone. Now jumping into each requirement and things that we have learned by running dynamic simulation on our test setups. So we have designed for PRC-29 around 8 to 10 simulation cases for requirements R1 and R2.1. How we do it is that we apply the LVRT and HVRT curve of PRC-29 in tables 1 and 2 in attachment 1 at the POM of the plant. And then we look at active and reactive powers at the POM. For R1, we want to identify if the plant is able to ride through all these voltage curves, all these voltage dips. And for that, we look at active power. My recommendation is to just look at active power and not reactive power, since you might see a case that active power goes to 0, but reactive power is not 0. And then you may wonder, okay, what's happening? Maybe it's not a trip. And then when you go and see and try to find out the reason, you see that the cap bank is generating reactive power. So I would say the safest quantity to look at is active power. And also you can always look at your simulation log and see if anything has tripped. One important factor that I want to really emphasize, and I've seen a lot of people do that and ask us why you guys are not doing, is that do not do a curve comparison. So this is an approach that I've seen a lot, that people put the PRC-29 LVRT curve on a figure and then put the under voltage and over voltage protection settings of, let's say, inverter and the feeder relays and HV relays on the same curve, and then say that, okay, if the relay curves are outside PRC-29 curve, then it's a compliance. And that's not technically correct, since all of those, each of those voltage curves are at different locations across the plant. And you need to take into account the voltage variation or voltage increase or drop that the impedances across the plant are going to cause and shift those curves around. So, and you're not seeing it. So that voltage change can shift those curves to come inside PRC-29 curve, and you're not seeing it. So it's important to run a simulation to capture that offset as well. Another thing is that make sure to set up the case such that the exceptions in requirement R1 do not apply. As JP mentioned, there are 4 exceptions for R1, including phase angle jump and V over F changes. So if you want to apply LVRT curve, make sure that you just change the voltage magnitude, don't change the phase angle of the voltage, and keep the frequency fixed at 60 Hertz. That's going to make it easier that if you see the IBR plant tripping, then you know that it's not caused by those exceptions and it's caused due to something that needs to be investigated. The other thing is that we've seen that the under frequency and over frequency elements trip during this test. And the reason is that the PSSC and PSLF engines, like specifically, are not able to calculate frequency when the voltage goes to 0 at this point. And they kind of cause an unrealistic under frequency and over frequency tripping. So to capture that, you may want to disable under frequency and over frequency protection across the plant. Another thing is that, which is very important, and is that if you see the IBR tripping, what you do is that you go and find the relevant protection element that caused the trip, okay? And then don't stop there. What you need to do is to disable that element and then run your simulation again. And the reason for this is that if you just stop there, you're going to just see the first layer of the issue. There might be another under voltage element that wanted to trip but did not have enough time. And once you disable that first element, you're going to see that second element that's going to again trip the plant. So I've seen cases that we have done this like 3 times and we have found like 3 faulty elements. So this is very important to do. The other one is that if active or reactive power do not recover, a partial trip may have happened. So be careful with that. And that's also a violation of R1 and R2.1, since these 2 requirements want active power to recover to the pre-disturbance value. Julia, I think I'm at my time, but I have quite a few more slides to cover. I'm going to try to wrap up fast. Yeah, but sorry if I go over time too much. Then talking about R2.2 and R2.3, these requirements are about active and reactive power priority. One thing about these is that in PRC-29, in the language of R2.2 and R2.3, what you see is that it talks about active reactive power. And while in the technical rationale document, it talks about active reactive current priority. So it kind of caused a bit of like confusion for us on which parameters we need to investigate and monitor. So since in the rationale document, it's mentioned several times that PRC-29 is moving along the IEEE 2800 standard, so we went with the active and reactive current priority mode. And for these 2 requirements, we calculate active and reactive current at the inverter terminal and focus on those to investigate if the inverters are operating in Q or P priority modes. So analyzing and understanding if an inverter is correctly implementing active or reactive current priority is very complex. So again, we went to IEEE 2800 because they have a very clear definition of what is active or reactive current priority mode. As an example, for reactive current priority mode, that standard says that reactive current should have access to the entire current capacity of the IBR and take whatever it wants, and then anything remaining is going to go to active current. So to identify this, you can do it like different ways, and depending on you have a generic model or a UDM. For generic models, I would say go and check for the PQ flag in the settings of the model. That might be available in the UDMs as well. That can give you an idea of what the inverters are operating, which PQ mode they're operating in. And then calculate the expected value of reactive current or active current. As an example, if the inverter is following K-factor diagram, you can calculate reactive current by multiplying K-factor by the voltage drop and see if that entire capacity is allocated to reactive current. So that's going to be reactive current priority mode. If reactive current is curtailed to some value below that value, then that's not a reactive current priority mode. If we don't have any of this information, the only way that we can verify this is by just looking at the general pattern of active and reactive current. If you see that active current decreases and reactive current increases for LVRT case, and this general pattern keeps continuing, then that's reactive current priority mode. And for HVRT, active current remains the same, but reactive current drops. That's again an indication of reactive current priority mode. So yeah, current limiter setting is also important. As I said, if that curtails reactive current. And also another factor is the current blocking mode. So make sure that that is implemented correctly in the model, and check the inverter manual and make sure that it matches what's in the field. If you see both active and reactive currents go to 0 here in this permissive operation region, that's an indication of activation of current blocking mode, and R2.3 wants that mode to be restarted within 5 cycles at most. So you want to be careful with that as well. And then R2.4 and R2.5 are about active reactive power recovery. A few points here as well is that how we approach it is that we apply 100% voltage dip at the POM of the plant, and then we look at active and reactive powers and how fast they recover and how smoothly they recover. For R2.5, PRC-029 wants a 1 second time window for active power recovery. The way we understand this requirement is that this 1 second is for active power to restore, and it does not necessarily mean that it has to settle, and that's totally our understanding. And based on our experience, 1 second is not enough for active power to settle fully. So if active power goes from 0 to 1 and then it has some overshoots and it takes some time to settle, we consider that as a pass. And then another factor that is very important is that this 1 second time window starts after the voltage returns to the continuous operation region, which is 0.9 per unit, sorry. So some people, I've seen that in their studies, they consider this fault duration into this 1 second time window. So as a standard clearly says this 1 second starts after the fault is cleared. And another factor that I've seen specifically in PSSC and PSLF are certain spikes that you may see in active and reactive powers, like this one here or this one here. Spend some time on these spikes and make sure that these are real spikes, because again, when the voltage is 0, PSSC and PSLF engines may face some numerical issues in terms of solving the equations in the circuit. So you want to make sure to see if these spikes are actual and real, and maybe you can check that with EMT models. That's a good approach, or if you see that in MQT reports of the plant. Also, if you see that active or reactive powers do not recover, double check the PPC settings, because that's the one which is in charge of active reactive power recovery. For requirement R3, frequency write-through, we do a curve comparison. Since unlike the voltage, this is a universal parameter, so you can put all these FRT curves on the same figure, and if the as left settings of the relays and inverters are outside the PRC-29 curve, then that shows compliance with the FRT side of R3. One point that I've seen a lot and I want to highlight here is the case where 2 curves overlap, like something as you see here. Different approaches can be taken here. Some may say like the as left settings of the inverters in this case is not going to operate for this 57 hertz, and it's set to like 5699. It's like less than, and it's not less than or equal. But how we see it is that we want to flag this and ask the generator owner to change that relay setting, because there's always like a small possibility of measurement error, and this can shift this curve inside PRC-29, and then that's going to cause the plant to trip. So we want to stay away from that. That's why we want to highlight that in our studies. The other thing is that check the relay setting files, and this is very important to make sure if under frequency and over frequency and under voltage and over voltage are included in the trip equation of that specific relays. And then you want to have the curves on this figure, because there are cases that these elements have been activated just for the monitoring purposes, and they're not actually tripping the plant. So you want to check the RDB and URS files to make sure that they are in the trip equation. And make sure to ask the generator owner to give you the most recent as left settings of the plant, and do not rely on the previous reports like PRC-24 or PRC-19 reports. Also, for the rock-off part, since this functionality is not typically implemented in PSSC, PSLF, and even some PSGAP models, we don't run simulation for this, and we rely on the documentations from the OEMs to see if that plant is meeting the rock-off requirement of PRC-29. And finally, the last requirement, which is not an official requirement of PRC-29, but it's included in, I think, item 8 of attachment 1 of the standard, that says that the IBR is allowed to trip for more than 4 consecutive voltage disturbances. So how we see it is that it's not allowed to trip for 4 or fewer voltage disturbances. So we have a specific test case for this one as well. And this is the curve that we apply at POM for this case. So one important factor about this is that although PSSC and PSLF simulations can be run for this test, and that's what we do as well, it's not generally recommended, since this consecutive voltage disturbance right-through functionality is not typically modeled in like phasor-based softwares or even in EMT software. So you want to reach out to the OEM to make sure if that's implemented or not. And if running a simulation, you want to make sure that these 4 disturbances remain within that 10-second time window that PRC-29 has, and also allow sufficient time gap like in between each voltage disturbance to have a realistic simulation scenario. IEEE 2800.2 recommends a 20 cycle gap for this specific requirement as an example. And then make sure to refer to the documents to see if your simulation results make sense. So just to summary, these are like some highlights and the important steps that need to be taken when doing a PRC-29 analysis. First one is to verify the as left settings with the different parameters in PSSC, PSLF, PSGAT, EMTP models of the plant to make sure that you have good trust in that model. The second one is that both EMT and RMS tools can be effective for doing PRC-29 analysis. And also another factor is that do not just rely on your simulation results. Make sure to check those with any documents that you find about the plant and the OEMs as well. And then an ongoing collaboration with the OEMs is going to allow to meet the essential technical and regulatory requirements of PRC-29. Another thing which is very important is to store, retrieve, and analyze all the documents that are available for that plan. That can save a lot of time, because that first stage of gathering documents, that can take a long time. So if you have everything categorized, that can significantly increase and save time there. And the last point is automation. Automation can be really helpful. Like at Elevate, we have almost automated, I would say like 85% of this entire analysis. So it automatically runs this simulation, generates figures, and gives a report. That can save a lot of time, and the engineer can focus on the actual work, which is analyzing the results and coming up with recommendations. Yeah, thank you very much. And once again, sorry that I went over time. And I hope you found this helpful. Yeah, thank you.
Thank you, Amin. No, it was great information. I wanted to let you go through all of it. And I didn't want to cut you out. So let's go ahead and go with questions. There are a lot of questions. And the first one's kind of explanatory questions that people have, and I think JP, it's probably to you primarily. The one question was about where does PRC